Dear ladies and gentlemen, dear all, good morning, good afternoon, and good evening. And welcome to the WinGD Ammonia webinar 2025. My name is Benny Hillström, and I'm the head of market development at WinGD. We will, in the next 45 minutes, give you some insights of the WinGD two-stroke ammonia engine technology. And today, we have the honor of Mr. Marcelot and Mr. Fabio Cococetta to present concepts result of the WinGD ammonia engine. But before we start, I'll just inform you that we are more than 600 people online, so microphones will be muted. But if you have any questions, you are welcome to put your questions in the chat box, and we will, in the end of the presentation, try to answer as many questions as possible. Okay, why ammonia as a fuel? Ammonia is an interesting fuel for shipping because it has the potential to significantly reduce greenhouse gas emissions compared to traditional marine fuels. Let me present a few key reasons why ammonia is getting attention in the maritime industry. Ammonia, as many of you most probably already know, does not contain carbon. So when burned, it does not produce carbon dioxide, making it an attractive option for decarbonization of shipping. Ammonia has a higher energy density than hydrogen in liquid form, making it easier to store and to transport. It's also easier to handle than liquid hydrogen because it does not require extreme cryogenic temperatures. Ammonia is already produced and transported globally in large quantities for use in fertilizer production. This existing infrastructure could be adapted for marine fuel supply. Ammonia can be used in internal combustion engine, which we will hear more about in a few minutes, offering a multiple pathway for its use as a maritime fuel. The International Maritime Organization has set targets to cut shipping emissions, and ammonia is one of the leading candidates to help the industry to meet these goals. However, there has been a number of concerns and consideration on this pathway of ammonia as a fuel in the shipping industry. Ammonia is toxic, and it is corrosive, and it requires carefully handling and safety measures. There's also been considerations and concern about emissions. When combusted ammonia produce nitrogen oxides, which required mitigation technologies. There have been other concerns like the magnitude of ammonia slip and N2O gas emissions. But all these are being tested, and we have now the pleasure of giving you some of these results today. Another concern has been, is ammonia actually available as a fuel? Ammonia today is most likely being produced by using fossil fuels, which we normally call gray ammonia. But in order to become truly sustainable, green ammonia is needed. However, green ammonia requires renewable energy. That is a little difficult to scale up fast. The bottleneck is that renewable energy. But there are alternatives to that. For instance, there are blue ammonia, which could be easier to scale and could be cheaper going forward. Despite of these challenges, ammonia is a promising alternative fuel for shipping, with ongoing research and pilot projects aiming to make it a viable part of the maritime energy transition. WinGD has been testing ammonia as a fuel for combustion since 2021 and have now developed ammonia fuel two-stroke engines from small bore X52 to the mid-bore size of the X72, and will deliver these engines throughout 2025. Mr. Marcel Art and Mr. Fabio Coccocetta will now go through the WinGD journey of ammonia and give insights of the WinGD concept, development, and results. So, Mr. Art, the floor is yours.
Thank you, Benny, for the introduction, and welcome everyone also from my side. As you have heard from Benny's introduction, we have made substantial progress with the development, testing and validation of our ammonia engine technology, and we're very keen and eager to present you some updates, some latest results, and where we stand with the development and introduction of our engines. In my first part, I will cover a bit more general part of our portfolio, ongoing projects, but also explain a little bit more on how the design concepts look like of our engines. My colleague Fabio in the second part will then also give you some more technical details, including latest test results of the engine. So let's go into this, and would like to start with an overview of our engine portfolio. What you see here is an extract of our engine booklet that represents the commercially available engines that we have available to our engine builders. You can see the typical LNG and conventional engine portfolio here on the top and bottom. And you can also see that on the ammonia and LPG side, we have a number of additional engines that have made their way into our official portfolio as of this year. Namely, on the ammonia, it's the 52 to 82 bore engines that are available commercially for contracting and for commercial projects. And then on the LPG side, and that's probably new to many of you because that's just recently been added, we have introduced the LPG burning versions of the engines in the 52 and 62 bore range, and we'll see a little bit more of that as we go. I'd like to give you a brief overview of the references that we have secured with our XDFA engine types, and as you can see from this slide here, we have totally contracted a number of 30 engines so far in commercial projects. They're covering the 52, 62, 72 engine types. You see the number of engines listed there also, and a few pictures of the specific projects. I guess many of you are aware of those because they have all been publicly announced. You can see, for example, the MGC on the top left that is coming with the 52 bore ammonia engine, bulk carrier series 210K bulkers with the 72 bore, then the top right Alframax tanker series with the 62 bore engines, and the others come with the 52. So a number of projects that are contracted are in the pipeline under preparation for production and delivery. Looking at the timelines here on a very simple time axis, you can see that the 52 and the 72 DFA are to be delivered to shipyards from mid of 25 onwards. We're in April now, and very clearly you see that we are approaching a significant milestone here with first commercial ammonia engine deliveries to shipyard very soon. Works are ongoing. First engines are actually about to be tested at the engine builders now, test beds. And as usually the case with 6 to 9 months between engine delivery to shipyard and vessel delivery, you can see that by early 2026, we expect to start having first seagoing experience with these engines. A few words on the collaborative approach that we use here for the development of the ammonia engine as such, but also the related auxiliary systems, such as, for example, the fuel supply systems. So what we do here is that we have a similar concept as what we have developed for LNG dual fuel engines. which is that we do provide specifications and requirements for fuel supply systems, for example. And then any shipyard, any potential maker can develop a system that can be used in connection with our engines. What we have on the XDFA is that we have this, what we call fuel valve unit, which is the interface to the engine, so between the fuel supply system and the engine. This fuel valve unit is kind of an approved component because it includes all the interface connections and controls. But other than that, we are open to work with many different partners, and we have done so. And there is a good range of supply systems available already today. A few words on the safety side and the developments that we've done there. I'd like to highlight here that we have been working with classification societies basically from day one in the development of this engine technology. This has also resulted in the submission of the first approval in principles for ammonia engine designs that we have received from a number of classification societies, as you can see here. And throughout the journey, we've also gone through a number of hazard studies. We have, together with classification societies, worked and reviewed our safety documentation, and we have also introduced design updates that were implemented as part of an iterative process as we have developed the safety documentation. And one relevant document I'd like to mention here is the one you see to the right that we call the engine safety concept. That's a document that summarizes safety principles and procedures related to design, installation, and operation of the engines. And that's also an outcome of the hazard studies that we have done. This file is publicly available on our webpage, and you can find it there. Still a bit more on the documentation side, and I think that's an important thing to be understood, that on our webpage, we have an updated webpage that includes what we call an engine selector. And you can see from the print screen here, the page allows you to select a fuel type, vessel type, and it will automatically give you a proposal of applicable engines, under which you can download all the relevant installation-related documents. So, for example, for shipyards or ship designers, or also owners, we have a number of relevant documents online. For example, the installation manual, the installation drawing set for the planning and integration of the engine in the ship design, and the safety concept as mentioned before. There is a link at the bottom here that you can use to access this section, and all material publicly available. The same goes for our performance data, and we do have our tool that we call General Technical Data, GTD. It's a publicly available tool that can be used to generate project-specific performance data, so all the fuel consumption figures, exhaust gas data, ancillary system capacities, for example, can be generated for project-specific types. In this program, we have currently included the 52 to 72 bore engines, ammonia engines, and we will add, other engines as we go. I think it's important to mention here that the performance figures that we show in GTD can be fully guaranteed, same as for other engine types. And as we will see from Fabio's part of the presentation, we have very good results in terms of engine performance from the test engine that fully confirm that the data we have here is reliable and valid. On a design concept, I'd like to highlight one simple thing, that the ammonia engine is not a completely new animal, but is actually fully based on the standard diesel engine design, the conventional engine design. So it's a conventional engine with an additional injection system on top, pretty much. Of course, there is a few safety-related features and functions that are added, but the base engine design is very much the same as on the diesel engine. We're using a diesel cycle combustion for burning ammonia, and that also means that we have diesel-like efficiencies in both fuel modes, ammonia and diesel operating mode. We'll have same power output in both modes, and same as on a conventional diesel engine, and many of the the diesel engine principles apply. Also, we use the same standard proven emission abatement concept, which is SCR for Tier 3 compliance. That's our standard technology on diesel engines, and the same is applied on the ammonia engine as well. So a diesel engine with an additional injection system, and looking at the injection system in a bit more detail is shown in this illustration here. You can see that we are using kind of a pressure amplifier type injector for pressurizing and injecting ammonia into the cylinder. What you see here is the setup of one cylinder. So we have 3 ammonia injectors that go on top of the existing diesel injectors. And the injectors are hydraulically driven. So you see the yellow lines, they are representing the hydraulic actuation oil circuit. So we're having oil pumps that deliver actuation oil to the control valve unit that you see to the right. On the control valve unit, we have individual solenoid valves that control the injection of each individual injector by feeding oil to the top part of this pressure amplifier piston. Ammonia is fed to the injector to the lower part of the piston at a relatively moderate pressure of 85 bar, and is pressurized when the hydraulics is pushing down the pressure amplifier piston, and then injected into the cylinder. One major reason for selecting such concept is that the ammonia is only pressurized in the injector itself. That means there is no high pressure pipes, no additional pipe connections that could leak and represent a safety risk. Another interesting thing is that the injectors can be controlled individually in terms of timing and duration. So we have the full control over each injector, which is a great benefit of these electronically controlled engines. This here shows a typical arrangement on the example of the 72-bore engine. If we look at the picture on the top right, you can see the yellow part is the actuation oil part, green are the ammonia pipes, and the injectors are also shown there. You can see that the design is fairly slim and compact, and one of the major criteria for the design was that the system needs to be easily maintainable by the crew, and that's also the concept here, that the crew can maintain, overhaul all the components by themselves and don't need special service engineers attendance. With that, I would like to go to my last part, which is the XDF-P. P stands for propane, or actually the LPG burning type of this engine. So far, WinGD has not had an LPG burning engine in our portfolio, and the reason was that we did not have a liquid gas injection engine design so far. With the ammonia engine design, that has changed, and that makes it very simple and reasonable to also have an LPG burning version of that engine type. And what we have here is that we have a very simple modification of the ammonia engine by adjustment of the hydraulic volumes in the injector that allow to optimize the injector for injection of LPG instead of ammonia. The target segments here are VLGC, VLAC vessels, or MGC, so the typical gas carriers that actually most of them burn LPG at this moment or upon delivery. With this design, because the design is fully based on the ammonia engine design, it's possible to very easily upgrade the engine to ammonia burning in the future by only replacing the injectors and upgrading the control system software. So we're providing a future-proof and very flexible solution to gas carrier operators that allows them to switch from LPG to ammonia whenever they think it's necessary. And for first engine deliveries for this technology, we target end of 2027, which fits well with current new building projects. So if you have any interest, any questions to this technology, please approach us, and we're happy to also look at the application optimization with you. With this, I would like to hand over to my colleague Fabio. He's already on stage. Thank you very much.
Thank you, Marcel. My name is Fabio Pocetta, Product Manager Engines. And today I would like to introduce you to our WinGD validation process for the ammonia technology, and also recap on some of the results we have achieved. So back in 2022, we said combustion tests were running in WinGD with the aim of optimize the combustion layout, as well as to derive the technical specification for the design team to design the proper injection system. After having got the prototype drawings, we started with a manufacturing process at our sub-suppliers. And then in parallel, if you look at the, let's say, row number 4, we had an hydraulic rig test, which were able to test components during the manufacturing process, so early components out of the production line, to test them and to provide some feedback to the suppliers to make corrective action until we achieved basically the specific expected performance from the components. The hydraulic rig test was also used to basically achieve the system performance, because on these hydraulic rigs we can mount basically the entire injection system and test it and characterize it. Once this was done, we started with full-scale test engines. The first step was on the RTX6 engines we have here in Switzerland. We tested on the real engine operating condition, the injection system, so vibrations, high temperature from combustion, as well as, of course, combustion products. So after the 100% load was done and the test was considered passed, then we basically mounted another injection system, a twin system, like the one we had on the RTX6 engine on a full-scale ammonia engine. And then we started testing the load step by step up to 100% load until the engine performance were achieved. So we got the first tuning of the engine. With this information now, we are preparing the last test, which will be at the engine builder site. So we are preparing basically the factory acceptance test, and we will run some specific WinGD tests before that time. The last milestone will be the engine delivery to yard in June this year. Okay, so I think it's worth to mention, even though the webinar is ammonia, that the same validation process we used for methanol technology development. So basically, the spray combustion chamber, as you can see here from the pictures, top left, then hydraulic rigs used in this bore size 92 for this 10X92 DFM engine, the first methanol engine from WinGD. Then full-scale test engine on the bottom right of this bunch of pictures. And then the 10X92 DFM at CMD. That was the process. And if you look at the timing, the commissioning of this engine started beginning of December 2024, and the factory acceptance test was 1.5 months later. And roughly 2 months later, the type approval test was done with no comments from classes. So this is not a surprise. We were working with classes since the early days, in the early phase of the development, to share our technology concept and to correct and address all the recommendations from classes. That was done also for ammonia. Okay, so next slide instead is coming back to the XDFA engine, so ammonia engine. We will go through a bunch of performance numbers. So first of all, Marcel already told you that the engine efficiency was same as diesel. So we confirm basically the GTD data which we published time ago. We also observed a very good combustion stability at every load. You can see a plot in the center of this line, the bottom center of this slide, where cylinder pressure over crank angle is reported. It seems a pressure cycle of a cylinder unit, in reality, they are 100 cycle plotted, which means the NH3 standard deviation was very good, similar or better than diesel. Regarding greenhouse gases, we made a calculation for your reference here over the 3 cycle, so IMO weights we're applying. Basically, we said that on the right side of this slide, you see the blue bar is diesel engine, make it 100%, and the ammonia engine, so on the right side, is achieving more than 90% of greenhouse gas reduction. Another interesting, let's say, view we have on this bar is the purple bar, which is representing the N2O contribution to greenhouse gases. The rest is basically diesel pilot contribution. So to achieve such kind of reduction, we basically use the spray combustion chamber at the beginning to really optimize the combustion, minimize N2O. So we measured below 3 ppm, thanks to our optimum combustion. And also the pilot, the diesel pilot energy share was below 5% at 100% power. So this, by these 2 measures, we could achieve these good results, basically. Now in the next slide, we are going through other type of emissions typical from ammonia engines, so NH3 emissions and NOx emissions. So we measured basically NH3 emissions less than 10 ppm engine out. The green bar that you see on the charts is the range we have measured, so below 10 ppm and below 2 ppm as a minimum. So that's the range we measured over all the loads. Also here, it was a target for the injection system design to reduce as much as possible those NH3 emissions, which are coming from design parameters, but also optimal combustion. The NOx reduction, which we observed preliminary, now we're talking about tier 2 diesel data versus ammonia data, we observed more than 40% NOx reduction. So a lot of margin with respect to tier 2 and tier 3 limits. Regarding the emission abatement for XDFA, we don't request any fancy catalyst technology. The SCR we use with the diesel engine works very well also for XDFA. We recommend high pressure SCR only. We don't need the specific catalyst for N2O because of what we said. So N2O abatement systems are not required. The N2O emissions are very low. And NH3 catalysts as well, like ammonia slave catalysts, are not requested in our case. We also offer the integrated SCR, ISCR, namely. We recommend the adoption of this design for 52 and 62 engines because it offers additional optimization potential for fuel consumption and reduce also yard installation effort. And being closer to the engine, it's also an advantage when it comes to ammonia engines, which are having typically lower exhaust temperature. We also can mention that early this year, so January this year, we got the type approval test for the ISCR. This was successfully completed with the participation of 8 classification societies. And also we are having a lot of running hours in the field with this technology, so it's a proven technology. Okay, now let me start with the plant side. So we discussed about the engine and the results. If you look at this schematic and you go to the light green box on the right side of the slide, you will find ammonia storage tank. From this tank, we get ammonia right straight into the engine. And during this the ammonia operation of the engine, we don't use the return line with ammonia. So basically, there's no ammonia in the return line. Now I will go to the purging process. If you look at the red box, it indicates a valve which is now closed. So for starting the purging procedure, we interrupt the ammonia supply, which is normally at 85 bar. We then depressurize the ammonia system towards the catch tank at 22 bar. And then we open the green valve that you can see, which is attached to the green box. The inert gas supply is open, and we use basically the inert gas to purge the system, to purge ammonia. This is, of course, done in a way, in a specific sequence on every cylinder and on every part of the ammonia injection system to ensure the removal of ammonia from all the parts of the system. But there is another step that we use. At a certain point, we close the inert gas supply, and we start to supply water into the system through a system which is called ammonia injector cooling water system. Basically, if you see the light blue box, that's the AEI CWS system, and water is flowing through the pipes, through the ammonia pipes. And the aim of this procedure is to remove any remaining traces of liquid ammonia which might be trapped in any cross-section of the system. And plus, we keep going with the flow of water through the injectors, also to cool them down and to improve the reliability of the injector when diesel mode is on. The system has been designed to basically do not exceed 10% of ammonia contamination into water, which means the tank at the end will contain a sort of an household ammonia solutions, which we normally use also for cleaning surfaces, for cleaning apartments. A bit of a summary of the operational steps. So in this chart, you see the power percentage in the x-axis. We have the ammonia mode, which is in yellow, and you see that the ammonia mode is offered in the between 25% and 100%. We are working also for an extension of the operating range towards 10% and even further low. The diesel mode is available from 0 to 110%, and the transfer to ammonia is in between 25% and 80%. Basically, apart from the diesel and the ammonia mode, we have also the possibility to have an ammonia standby stop. This is possible when we need to, for example, change over to diesel mode for a defined period. And there we discussed also this with classes, no purging is required. Ammonia system can remain ready to re-inject ammonia. But of course, if this defined period is too long, the normal stop is requested. So purging and the activation of the ammonia injector coolant water system is required as described in the previous slide. For maintenance work, to keep our crews safe, we use basically the normal stop, and then of course the water is removed by pressurized N2 and the system is depressurized. This allowed the crew to have high confidence level that ammonia is not anymore into the system. So to finish, that's my last slide. That's the innovation journey of the XDFA. We started in 2021, sorry, with the ideation phase. We went through the concept phase in 2022 with our test at the spray combustion chamber. And then we frozen basically the technology concept, and we tested this technology concept meanwhile in our commercial projects, which were running in parallel. So we ran pre-hazard study, hazard study, we corrected our design, and then we got in September 2023 the approval in principle for our concept. And then in 2024, as discussed, we started the validation of this technology. So I think a statement can come out from this slide that the ammonia engines are a reality. They are working, emissions are very low, and can be a great tool for the decarbonization of the maritime sector, as far as they can reduce very much the greenhouse gas intensity of any fleet. So with this slide, I finished my part.
Okay, thank you very much, Marcel and Fabio, for your nice presentation. I have, in the meantime, looked in the chat box, and there are many questions, and thank you very much for that. I have tried to see if I could put this as to different themes while you have been presenting. There is a number of questions related to safety and leakages. So maybe that goes to you, Marcel. How is crew safety ensured in case of an ammonia leakage?
Yeah, valid question. And as you say, safety is a concern that needs to be handled seriously. I think what we can say here is that we have applied many of the principles that have been developed by us on the engine side, but also by classification societies for LNG as a fuel in the first place. And one of them, one of the standard principles is that we have this gas-safe engine room concept, which means that all ammonia-containing piping and components are of a double wall design. And that means if there is any leakage of the inner piping system, it will go into the double wall annular space first, where we do have detection measures with ventilation and sniffers, and by that can avoid that a leak is going into the engine room directly. I think that's one of the major principles that we have applied, that we know works well from LNG dual fuel, and we have, by the way, also seen on the test beds we have run on the test engine. We have run specific tests to confirm that this system works well.
Okay, thank you for that, Marcel. But still related to safety, how about crew access to the engine room when operating on ammonia?
First of all, it from our side and from what we see also with class and what we have described in the engine safety concept, access to the engine room when running on ammonia is possible. We do recommend to minimize access to the engine room. So if not absolutely necessary, we don't promote people to go in there, but it is possible. What is necessary is that people wear PPE, so basically an ammonia sniffer, so for a gas alarm on person, and they carry a protective mask at hand, not on their face continuously, but at hand. So in case of a worst case leakage into engine room, which, as I explained before, should not happen, but in such a worst case, they would have protective equipment available.
Okay, and still concerning crew and safety, does WinGD provide crew training and operational support of vessels in service?
Yes, we do. Actually, crew trainings is something that is under development now. We're preparing for the trainings also for crew of the first projects. Those trainings will be provided through WinGD's global training system or setup. So we do have training locations, different locations for crew training. And ammonia engine operation and maintenance will be one of the standard trainings that we offer. The second question was about operation support, if I remember correctly. Also here we do provide operation support. I think what is to be mentioned here is that we think for all modern type engines, say dual fuel of whatever type, that have become more complex to handle and operate, we do see great benefit with the remote monitoring tools that we have available nowadays. Our engines have a data collection system installed as a standard, and we do offer remote monitoring and analysis tools, which we think on these type of engines are of great benefit because it allows our experts operation experts to monitor engine behavior and operation continuously. It allows to avoid any downtime or failure, because ideally we can find an issue before the engine has to be stopped, and it allows to help and support troubleshooting in case that is necessary. So we're fully preparing on that to be supporting owners and operators once these engines are in service.
Okay, thank you, Marcel. Then there are a number of questions around the performance as such. So let's try to start. SCR catalyst, is that a requirement to minimize the NH3 emissions, or how is that, Fabio?
Basically, we have seen very low NH3 emissions, as discussed, below 10 ppm. So the SCR is not installed there to reduce NH3 emissions, but it's, however, still required for the Tier 3 NOx emission targets. So both in diesel and ammonia mode. So SCR will be requested for Tier 3 operation.
Then also related to performance and behavior, I guess, of ammonia in a combustion engine. Ammonia has been said it's challenging to burn because it's a slow burning fuel. How does that actually apply into the two-stroke engine, Fabio? How do we see the combustion? Is that been challenged, or is it a steady, or how is the combustion based on our tests?
So I mentioned in my previous slide that the combustion stability was very good. Of course, this is not by chance. We ran extensive tests, especially on the pilot injection, together with ammonia injection, and also we optimized the layout so that the combustion stability could have been guaranteed so well. So for the connectability, I would say I don't see any problem. We have tested many noises even on the injection system, and the connectability was noises coming from components, tolerances, or dispersions, and the connectability was never a problem. So that the system has been designed to be robust in this case. Regarding the flame speed, so the fact that this flame speed is a bit lower than diesel, it's a good point. I mean, it is not difficult to burn, by the way, ammonia in the two-stroke engines, because two-stroke engines are typically having lower RPM than other type of engines, say four-stroke engines. So this will help a lot to develop this ammonia flame in the proper way. And in fact, we see efficiency which are really aligned with diesel. So the two-stroke engine, to summarize, is the perfect engine for burning ammonia.
Okay, thank you. Then, but that's also related to that. Maybe you could give some insights about the exhaust gas temperatures in the combustion, Fabio. Maybe you could also give some insights of that.
Right. So I mentioned in my previous slide that the exhaust gas temperatures were lower than diesel, and this is basically the physics of the engine, because the ammonia, when it enters the combustion chamber, has a large amount of latent heat to create, or at least needs a large amount of heat to evaporate, and this is reducing the temperature of the combustion chamber. And so the starting temperature for combustion is lower, and the exhaust temperature is also lower. By the way, when running ammonia, there's a limited need of economizer or steam production. In case it is needed, of course, we offer our standard steam production control for these specific cases.
Okay, thank you very much for your nice answers, and thank you one more time for all your great questions. We are about to run out of time, so let me try to wrap up. We have now demonstrated to you that we have been able to deliver technology, and we have three primary criteria for these developments. It was safety, and safety. And that's basically how we have been looking at this and have been dealing with this with the greatest respect of ammonia as a fuel. However, now it's here and we are ready to take next steps. For years, the industry have claimed that technologies have not been available in order to decarbonize shipping. Now with methanol and ammonia engines from WinGD, this is no longer the case. The technology is here, it's available, it's safe. So now it's fully up to decision makers at IMO and others to really see if they want to decarbonize shipping. There is no technical excuses anymore. So with this, I would like to thank you very much for joining our webinar. Thank you again for all your questions. If you have further questions or are keen to learn more or have other interest of the WinGD technologies, you are more than welcome to visit our website or contact us directly. I wish you all a great day. Goodbye.
Thank you. Goodbye.
Bye, everyone.